Hi, my name is Jeffrey Cohenauer, and this is my Lab 5 on the principles of falling objects and drag. The principle we're going to explore is drag and the effect of drag on objects of differing surface areas, but identical masses. We're going to need to take into account Newton's law and the Earth's gravity of 9.8 meters per second. Since we are modeling objects of differing surface areas, we're going to need to relate the lack of acceleration to a drag formula. The glow script model will be coded to account for the drag, and this model will be compared with the observed model for accuracy. For my analysis, I chose to drop a crumpled piece of copy paper. The paper dropped from a height of 1.895 meters. I know this because I calibrated the system with my own height of 1.88 meters. Would we normally expect this ball of paper to fall as quickly as a small pebble of the same weight? Most would agree not. Why is this? The obvious culprit in this situation is drag. We must account for this in our code. The first substitutions in our starter code are made by inputting the mass of the paper along with the force of gravity. The time constraint is set to the time of the last frame I analyzed in the tracker data. To account for the drag observed, a proportionality constant was used to ensure both the computational and the observed model displaced the same distance. The drag assumed to be acting on the object is known as turbulent drag, which is proportional to the speed of the falling object. Squaring the velocity of the object and multiplying by our proportionality constant models this drag in our data. Here we have graphs depicting the computer-generated motion with and without the effect of drag. The observed model is plotted along with both computational models and is labeled in blue on both. The chief differences we see when comparing observed data with our drag-free computational data is that the model without drag displaces a further total distance than the observed model in the same interval of 0.533 seconds. This indicates a higher average velocity. Both models display less linear accelerations than the observed model does. Here we have both computational models plotted together. We can observe the plots getting further and further away from one another as the object increases velocity. This is the observed model and computational model with drag up close. We see the data diverges in the middle of the set. Why might this be? The culprit could lie within data analysis, specifically choosing the center of mass at each frame. Given the increasing speed of the object and a relatively low frame rate of 30 frames per second, the object appears blurred in some frames. The best approximation of displacement in these frames is the center of the blur. Taking the center of the blur is, in essence, taking an average of the motion. This could partially explain why the observed data has a shallower curve. With a limited time frame to observe, drag doesn't make a profound effect. However, when observing velocity over a longer interval of 8 seconds, we can see how it can start to take effect. Notice the model without drag continues to increase in velocity at a constant rate, while the model with drag levels out after about 3 seconds. This shows the object's terminal velocity. So, what if we were to throw the object at the ground rather than just drop it? Would this initial added velocity affect the object's terminal velocity? Here we have modeled two simulated motions. The top motion with an initial velocity of -1 meters per second, and the lower motion with an initial velocity of -3 meters per second. Both models have the same drag force applied to them, so we can observe that both objects meet the same terminal velocity at about 12.8 meters per second. The only difference is that the thrown object will reach this terminal velocity a bit quicker. These results display the overall principle of drag and how it determines an object's terminal velocity based on its unique drag coefficient.